Hey everyone, I'm Alex. I'm lead of research at Distributed Lab. Yeah, and recently we started research on BitVM2 solution, and I'm gonna share some experience with that, some pitfalls we met, some achievements also like we reached. Yeah, why BitVM2? Because a lot of people are talking about BitVM. A lot of people talking like pessimistically that it's just a toy. It cannot change the future. It cannot support Bitcoin for like any computation you can imagine. Some optimistic people can say that that's the first way how you can organize some random execution top on Bitcoin. But yeah, some people just talking right now about which applications can be run top on BitVM2, about bridges, about rollups, about like arbitrary computations. Some people think that it's possible to launch, I don't know, spaceships using BitVM2 solution from like Bitcoin as a platform. But technical people are talking about what exactly we can do with BitVM2 solution right now. Because that's as any technology that's limited, and there are things it can support right now, but something isn't possible to do with BitVM today and in the future. So I will share my own experience and what exactly we have already reached with this technology. So let's do a quick recap. What is BitVM2 exactly? Just imagine you have some arbitrary program written, I don't know, for any language you prefer. The first step, you should divide that. So not why, but the first of all, you need to transformate that using Bitcoin script. Just imagine you have some code written on Rust or Golang, and first of all, you need to convert that to some Bitcoin script. So you can use only Bitcoin outcomes. Bitcoin script is limited, is very limited, and right now it's like more limited than before. It supports only basic arithmetic operations, for example, additional. So it doesn't support multiplication. It doesn't support some like logical operators, etc. That also there is limitations that you cannot inspect the transaction in the future. So Bitcoin right now doesn't support governance. Just imagine that first of all, you need to rewrite your code using very, very limited language. Just imagine you're successful with that. And the next limitation is you cannot execute the random length Bitcoin script within one Bitcoin block. So Bitcoin block size is limited for 4 megabytes, and it means that you can put all the limited readings inside. Logically, the next part is dividing the full program to some sub-programs and like receiving some intermediate states. The states are results of computation of these sub-programs. Then you need to be committed for these results, and for that, BitVM2 solution proposes to use Lampert signatures. That's not very efficient solution, and I will explain how we can reduce computation costs in this point. And we can describe BitVM2 solution via 2 ways. The first way is pessimistic, so you can use 3 types of transactions to support these arbitrary computations. And also BitVM2 solution propose a way how you can convert this flow to like very optimistic way by introducing 2 additional transactions. So let me explain how it works right now. So the first type of transactions is a claim transaction. It means that some operator can declare that this operator knows some value. This operator knows some program, and he should be committed for the result of execution of this program with this input value. But that's just a claim. I know that I can perform this program and receive some particular results. Then if everything is going well, so if the operator wasn't challenged by some party, after some time log, it can return their money. But at the same time, any person can challenge this operator. Challenging transaction provides you an ability to push an operator, reveal all intermediate values, and committed for this state. So if you challenge an operator, it must reveal a third transaction. A third transaction includes intermediate values and also commitment for these values. This should be verified by appropriate public key in the future. If operator publishes a third transaction, there are two ways how this transaction can be spent. The first way, that's like a regular payout. If nobody disapproved this transaction, operator can receive their money back. But if, for example, the some subprogram was executed very incorrect way, it means that any person can create a disapproved transaction, send that to BitVM2, and reveal that particular subscript was executed incorrectly. If that happens, this blamer or disapprover can receive some reward for that. So yeah, that's a very famous scheme, how Robin Linus just imagined it. Yeah, and drawing how BitVM2 solution works. So yeah, here is the claim transaction. If everything is going well, you can initialize payout optimistic. In this case, yeah, everybody agrees that the script was executed correctly. If not, there is some challenger that should publish challenge transaction. Then operator should publish a third transaction and also receive their money if nobody disapproves that. If somebody disapproves that, he should reveal the particular subprogram that should be disapproved and also execute this program. If this subprogram returns false, it means that he didn't prove the violation within this computation. Otherwise, this challenger can receive reward. So yeah, we prepared initial plan of what exactly we could do with BitVM2 solution. The first of all, we wanted to realize the general split function. It means if you have some arbitrary Bitcoin script for any length, there should be a function that allows you to divide that very proper way to particular chunks and with some assumptions about this chunk size and additionally some assumptions about stake. I will explain what does it mean. Then we decided to realize some functions, some general functions using BitVM. So yeah, everybody talks about realizing some verifier, some snark verifier or start verifier using BitVM2 solution. But we decided to start with some easy solutions. So for example, we wanted to implement some multiplication function for big numbers, some hash function, etc., etc. Then if we are successful, we're gonna realize a general snark verifier function, but honestly, probably right now that's not possible. Probably with some optimizations in some future, it will be realized. And then if everything is going well, we gonna realize a bridge demo. A bridge demo is like extension for snark verifier function, but the main goal is to put some particular state of accounting system within this like BitVM2 state machine, and then verify that particular transaction within this accounting system was executed and applied correctly. And this transaction can include some information about that some wrapped Bitcoin, for example, was buried. So yeah, let's talk about general function split. So yeah, we implemented this successfully, but we stuck with some limitations. So yeah, the idea sounds very easy. If you have arbitrary program, just divide that. But in the practice, there are several nuances. The first of all, stack size. we will talk about that. The next one, conditional operators. That's also a bit tricky to track these actions, to track this bytecode, not bytecode, but these operators. And also we had a huge problem with state commitments. Stack size. So Bitcoin supports only 32-bit values for arithmetic operations. It means if you're gonna have a deal with bigger values, if particular states, you need to dedicate several stack elements for that. For example, if you're gonna to make some calculations with 242, 44, for example, bit values, you need to dedicate, 8 elements, 9 elements for stacks. And also there should be additional operators that push this value into the stack and make some computation with that. Additional requirement that the max number of elements in the stack could be less or equal to 1000. So it means that you cannot publish just arbitrary state within Bitcoin script, and you should do everything within this limitation. So for example, it means you cannot build arbitrary lookup tables. You cannot do a big amount of pre-computations and put them within the stack. And yes, it's very tricky. It's very tricky, and sometimes that's not possible to run arbitrary program that consumes a lot of data using Bitcoin script. That's the reason why BitVM2 solution cannot suit any case. Then conditional operations. So there are several operators, OP if, OP not if, etc., that it's like flow control operators. And obviously you cannot divide your subprogram inside like this if blocks. So you cannot break these constructions, and it means that within some particular subprogram there should be a full if condition. It means that you also should, when you're writing the program, you also should think about how to write it properly with if blocks that don't exceed 4 megabytes. If you're successful, if you can write this program, it should work using BitVM2 solution. If your if block exceeds this value, you will not be able to run that. And the next one, as I said before, when you are publishing the intermediate states in a certain transaction, later you need to prove that these commitments for these intermediate states, if they satisfy predefined public key. So when operator creates a subprogram, they should generate the set of secret and public keys that allow in the future to prove that this computation was performed correct. And in original BitVM2 paper, they proposed to use Lamport signatures, and the signature means that you should generate 2 key pairs for 1 bit value. So if you're gonna use this approach directly, it means that for each 32-bit state value, appropriate public key will take 1,000 and more than 1,200 bytes. That's a huge amount of data if we are talking about Bitcoin. But continuous, there is a way how you can reduce these costs. You can use internet signature. Internet signature allows you to break the message to particular chunks and generate a public only one key pair for particular chunk in this message. So you can reduce the full cost of verification, the state, from more than 2,000 bytes to, let's say, 600. That's significant improvement. And we also implemented that. We implemented pessimistic scenario, as I told before. Pessimistic scenario includes creation of 3 transactions. The first one is a third transaction that commits for some states, The next one is payout transactions that allows you to take money after some time lock. And disapproved transaction that allows you to reveal the part of top tree. Top tree is like a tree that includes all subprograms as in leaves. And when you want to disapprove some particular transaction, you need to publish this subfunction. You need to publish a Merkle branch to prove that it's included into the tree, and then you need to execute internal script. So we also implemented that, and it looks the following way. So you can see unspendable taproot, taproot key, and also mass tree. All leaves include different disapproved scripts, and their amounts depend on the size of the full program. And the last scenario is this payout script. There's a script that will be called by operator if nobody proved that some particular state was executed via incorrect way. Yeah, good news. We re-emulated OpenMul. So right now, yeah, we have built a library that allows you to use OpenMul operator. It was deprecated several years ago. This operator was like very simple. It can take two values from the stack, multiply them, and return the resulting value back. It was deprecated, but right now you can use that as well. We are gonna publish a report probably next Monday or Tuesday with achievements and with a reference to the library. So right now you can multiply different values by 3. Bad news, early it took 1 byte per operator. Now you should send 3 transactions in Bitcoin for like executing this computation. Additional example, we took square Fibonacci sequence script from original BitVM repo and also emulated that using BitVM2 solution. And yeah, you can calculate. So the program looks as following. You have 2 numbers and you need to calculate the next number that is sum of the previous number squares and the number before squares. So yeah, in this case, this approved script includes almost 300 kilobytes. So it's possible to put that within 1 block, within 1 transaction. And yeah, the total size of the program for n equal to 128 is 35 megabytes. But as I said before, it's possible to break that to different subprograms, and each program for disapproval will take only 290 kilobytes. So yeah, that's also successful. Also, I will share materials after the presentation. What we're gonna to do our next day, we wanted to build the script for multiplying big values. So yeah, everybody knows that for successful snark verification, you need to operate within big fields. For example, with 254-bit values. So the next step is supporting this like large multiplication. It will take a huge amount of like memory, and yeah, there are a lot of assumptions, but at least that this component will be very useful for not for arbitrary operations, but for operations required for verifying snark proofs. So yeah, alternatively, a lot of teams also are working with this direction. For example, yeah, Alpen Labs, they also did a lot of investigation of BitVM2 solution and also published several papers with explanation of limitation of BitVM2 with potential vectors of increasing efficiency with BitVM2 solution, etc., etc. So also I will leave some materials and yeah, very good to read them. Yeah, that's it. Okay, thank you for the time. Yeah, bye bye.